Dobrý den všem přeji. Vítám vás v místnosti Gutenberg, pochopitelně nejlepší a největší místnosti tady na DevFestu. A vítám našeho prvního speakera. So, Danut, it's yours.
Thanks. So hello everyone. Welcome. Good morning. How's everyone doing? Did you guys enjoy that? I don't speak Czech, so I didn't understand a word of the whole thing with the wizard and everything, but I still found it really funny. So I don't know what happened. It was brilliant. I don't know. So my name is Danut Enachioiu. I'm a software engineer with Google, and it's the second time this year actually that I've attended one of these DevFest events. I was also in Pardubice earlier this year. Anybody here saw my presentation in Pardubice? You did? Wow, quite a few people. So there you go. Thank you for your loyalty, I guess. So the reason I make my way here to give you guys these presentations is that I love talking about things I'm passionate about. And today this is related to App Engine. Anybody here know what App Engine is? Let's see. Let's get a... Wow, that's pretty good. That's pretty good. So for the others, App Engine is a platform for web development that's built by Google, and it runs on Google servers, and it allows you to build web applications, web services, things like that, and they will all run on Google's cloud, and they will all be very scalable because of that, right? So App Engine, we use it a lot at Google internally as well. Most of our internal applications are developed in App Engine. And so when I joined Google, I was assigned to work on an App Engine application. Okay. Well, it turns out before Google, I worked for Microsoft, and I worked in the SQL Server team. So I was very much in this kind of traditional relational database mindset, right? SQL Server, right? I knew relational databases. So I come at Google, and I'm working on an App Engine application, and it's using Datastore instead of a relational database. And that was a bit of a shock. It was a bit difficult for me. I found it initially to be quite confusing. I found it to be frustrating, so limited. Now, if you ask me today how I feel about the data store, I'm going to tell you it's powerful, it's simple, straightforward. So how exactly did that happen? Well, it's a bit of a long story. We're going to go a bit through it. The idea is this talk today is what I wish somebody would have told me when I started using the data store. So hopefully I kind of can save some of your confusion and frustration if you start using it. Just to check, who here has actually used the data store for any of their programs? Okay, quite a few. Well, hopefully you guys will also learn something new. If not, I'm also available for more difficult questions afterwards, right? So let's see. So first off, my clicker isn't working. Well, that's a good one. It works closer. There you go. So first off, the data store itself, what is it? Well, you might be surprised to find out it's a way to store data. Mind-blowing, right? We have a way with names at Google, right? Anyway, so it's a way to store data, and it's the main way in App Engine. Now, recently, it's also been launched as a separate cloud platform product, but that means you can also use it for applications that don't run on App Engine. But the point is, once you come into App Engine, this is kind of your main way to store data. And if you read about it, try to figure out what it's about, the first thing you'll see is it's schema-less. So what is that, schema-less? Well, if you kind of think of the traditional table from a database system, looks a little bit like this. You got a very fixed set of columns, and all of your rows, which have a nice defined order, have every column in your table, right? Well, schema-less data store is something like a bit like this. Like this, there you go. I can store one pet and say I want to store a type, a name, and a breed for it. And then I can store another one and store a type, a name, an age, and the length of its whiskers. And I can store a third one, which because it's a llama, it's really important to know the last time it was shaved. Remember that in case you ever raise llamas. So we can have each of these entities have a different set of properties. OK, sounds good. What else? Well, the other thing about the data store, it's very good at scaling. That means it can handle a lot of data. It can handle a lot of users. It can handle a lot of queries per second. That also sounds good. The problem with this definition is it kind of puts people in two different mindsets when they get started. And unfortunately, both of those are wrong. The first mindset is that it's essentially a key value store. You give it an object with a key, it stores it. You give it the key, it gives you back the object. And there's a lot of folks who think this. I was actually talking to a friend the other day, and I was telling him I'm doing this presentation, and he said, I don't know, man. I always thought of the data store as a key value store, a big hash table. And it's not totally wrong. You can use it like this. You can use it exactly like just a key value store, but then you're ignoring the fact that it can also do amazing queries, pretty complex ones. So then you have the other camp. And the other camp are people who think, well, it's essentially a database, but it's schema-less, and it can scale arbitrarily much. And that's crazy, because if you could take a database and scale it and make it schema-less and still keep it a database, then the database software people would have invented that a long time ago. It would have been all of the databases servers right now would scale infinitely, right? So unfortunately, it's neither of this, especially if you consider it's a database and you come into it, it's going to be pretty frustrating. It's going to end up being disappointing. So let me try to kind of explain what it actually is. Oops, there you go. So this brings me kind of to my first big important piece of advice, which I just spoiled there, which is this. Unless it's appropriate. Don't use it unless it's appropriate. So guys, let's be honest here. Databases still exist. They are a very mature software. They have decades of engineering behind them. And they do amazing things. In fact, Google offers a Cloud SQL, MySQL version called Google Cloud SQL. Runs in the Google data center. It is replicated. It is fully managed by Google. Supports up to 100 gigabytes of data. It's actually quite good. So why would you use data store over this? Well, as we said, the data store gives you two things. Gives you schema-less, which is great if your application is kind of designed around that. And it gives you really good scaling. But the thing is, not every application needs to scale arbitrarily much. If you are developing an application for a small company, has 10 employees, and has maybe like 10 megabytes of data, you probably will not need infinite scaling. Sure, your company might grow to 100 employees, and your data might grow to 1 gigabyte. But it'll still be nothing for Cloud SQL, right? On the other hand, if you're writing a public application, if you're trying to write the next big thing, then don't limit yourself with Cloud SQL, right? If you're building a public application, you want it to get ridiculously popular. You want it to have, 1 billion users. And at that point, Cloud SQL won't make it. And at that point, you want the data store. And there's another thing here. A lot of people think, well, you know what? I'm not going to commit to one of them. I'm going to just build this abstraction layer around my persistence code. And I'm going to be able to switch from one to the other as needed. Nope, you will not. Well, actually, you could. You could try to do this, but these two things are so different that you kind of end up building your application around what features and limitation each of them has, right? When you try to switch at some point in the future, you'll find it really, really hard, and some things you used to do will become impossible or extremely expensive or extremely slow or all three. Well, anyway, right? So, oh, and there's another note for, kind of hobbyist developers playing with small, tiny applications with very little usage. It turns out the data store is extremely good at price scaling, even at the low end. So if nobody's using your application, well, almost nobody is using your application, it's probably going to be free or extremely cheap. Cloud SQL is not exactly that good at handling the very low end, right? OK, so let's say you've actually chosen to use the data store. You've chosen to use a bad clicker. OK, let me talk to you a bit about what's the magic in data store. And actually, the thing I like to say is there is no magic in data store. That's kind of the essential thing to remember. See, if you've used databases before, you're used to the magic. You send the query in, and your results come out. And in the meantime, the database might have scanned entire tables, might have built temporary representations of your data. It might have used indexes. It might have done all kinds of crazy things. And it produced your result at the end, which is great. It's pretty amazing. It does a great job when it works. But sometimes it doesn't. You don't really control this, and most of the time you don't really understand it. Some of you maybe do, but then you're kind of significantly above your average database developer. The thing with the data store is that's not the right approach to have when starting to use it. For instance, when I started with this kind of magic data mindset in mind. I came in and I said, I don't need to know how it really works. I just need to know the rules. Give me the rules, I'll send my queries, and it should work. Looked like the rules were really complicated, really frustrating. That's not the right approach. The right approach is understand the magic. It's simple enough that I hope to go through it in this presentation, and I have like 35 minutes left, I think. So that's the correct approach to learning the data store. Let's get started with that in mind. So data store is based on something called Bigtable. Anybody hear of Bigtable? Bigtable. Quite a few people. If you want to read more details about Bigtable, there's a research paper that explains it all. But what you need to know for this presentation, it's essentially a big sorted array. So it has a bunch of columns. The first one is a string, that's a key. And this array, this huge array, it's sorted by this string. Sounds simple enough, right? The thing that Bigtable does amazingly is this is really big. Like, they mean the word big in it. Just so you get an idea, all the data in all the applications that run on App Engine, all of it is in one Bigtable, right? So when we say this is Bigtable, it really is big, right? Now, say that I want to add some data to data store. I create a new entity. This is my pet llama. His name is Manuelito, right? I create this. I give it to the data store. I say, please store this for me. What it's going to do is it's going to insert this appropriately in the table so that it's still sorted, right? Somewhere between L and N, right? The prefix, identifies your app and identifies the kind of entity, but those are details. So tell me now, what can you do efficiently with a really big sorted list? Come on. Oh, come on. You know this. Sorry? I can't hear you. Could you say louder? Lookups, exactly. So the one thing you can do very efficiently with a big sorted table is find a particular key. So if we have the problem, well, can you find me Fluffy, right? It's really fast to find this. It'll do something similar to a binary search, and it'll find this in very little time, no matter how much data you have. Now, just understanding this allows you to, answer questions to yourself like, wait a second, if I have, instead of, 15 pets, if I have 1 million of them, will this be slower? Nah, not really. No. Remember, this table is already humongous. It doesn't really care about your own 1 million records. And besides, it doesn't matter because it's sorted, so lookups are really fast. Right. But what if you send to the data store, you want a query to find pugs, right? You have a property of these things, and you want the dogs whose breed is pug. How are you going to do that? Well, OK, back to question for you. Could I do it using this table? No. Do we get an yes? We got a no. Anybody get an yes? Guys, you are so careful. You're not going to get marks or anything at the end, and there's no achievements for correctly answering these. So the answer is, well, yes, technically, but it would be ridiculously slow. We would kind of have to, find the first pet, because we can do that, and then kind of go through each of them, load it, and see if it's a pug, and continue. So it wouldn't be efficient, right? Now, what we would need, if you actually try it, so it's very interesting, because if you try doing this, the data store will not let you. It'll just tell you, need index. We're going to get into what this wants, but this is a very important principle behind the data store. The data store won't allow you to shoot yourself in the foot, essentially. So what this means is the query you send to the data store must have an execution time that is proportional to the number of results, not to the amount of data you have. Okay, that sounds kind of academic, but in reality, it's pretty powerful, because that means while you're coding, if you write a query that works, and it gives you, 20 results, then you can pretty much assume it takes just as long as any other query that gives you 20 results, as long as it works, right? So you see what I'm saying? If it would take longer than typical 20-result queries, the data store won't let you. There's an exception to this, and I'll get into it a bit later, but in principle, this is what a data store does. So it wants an index, and in relational databases, indexes are a bit complex, and there's a lot of types of them, and it's kind of hard to get into all of it. But here, they're pretty straightforward. Let's just, think with me. What would you need in order to reliably find all the pugs quickly? Well, you'd probably come up with something like this, right? Just a list where you sort all of these things by the breed, and then it's pretty easy, because then you can do a lookup for, the first pug, find the first pug, and then all of the other pugs are just going to be next to it. So you go on and you find all of them until you get enough. Or if you love pugs and you never get enough pugs, that's a different problem. But there you go. You get all of these. OK, that sounds easy enough. The data store does exactly the same thing. The only difference is it doesn't copy the data again. It just kind of keeps the key of each data item, because it knows it can go back to the original Bigtable and find the data itself really quickly. So that's not a problem. What if I'm looking for pets that are black? Their fur is black. How would I do that? Well, we come up with another list just like this, but it's sorted by the color of the pet. OK, easy enough to understand. We can just find the black ones really quickly. Great. OK, new challenge. What if I want both? I want pugs that are also black. Well, you can't use either of these two tables, right? Because in the first one, not all of the black pugs are necessarily next to each other. They're kind of intermixed with white pugs or whatever. And the second one, not all of those black pets are pugs. Well, it turns out the answer is pretty simple. We need something like this. We need an index where we sort first by breed, then by the color, and then it's pretty simple to find all of the black pugs because they are next to each other. This is the essential property to remember about the indexes you create. The index must put all the results of your query next to each other, guaranteed. So you don't have to remember all the other rules. If you go to the Datastore website, it'll teach you these rules that go like, you know, if there is an inequality in your query, it must be the last item in your index definition, and crazy stuff. Just remember this. It must put all of your results next to each other. So let's do, this is called a perfect index, by the way. Kind of like the perfect storm, right? It's just it's a good thing, not like a storm, right? So let's do a little bit of a quiz for achievements. Not really, sorry. So the first quiz. If we're searching for black pugs, does it matter if our index is breed and then color, or color and then breed? Come on. No. Yes, great. Anybody a third answer? Maybe. There you go. That's it. So the answer is no, actually, because if you think about it, although the two indexes look completely different, you know, in the order, you know, black will be first versus pugs being somewhere lower and so on. If you look at how the records would look, the black pugs are still next to each other. They're in a different part of the index, but that doesn't matter. They're still next to each other. Both of them will work fine. Okay, question 2. I want pugs sorted by age. What index do I need? Come on. Sorry? Pug, actually breed, right? And then age. Okay, that's a good answer. Question, what if I put them the other way around? What if I say age and then breed? Does that work? No? We got a no? Do we get a yes? We got a yes, we get a maybe. Okay, so no, the answer is it won't. Think about how this one would look. You would have, if it's sorted by age first, you would have all of the 1-year-old dogs, right? And then one of the 2-year-old dogs and so on. But the 1-year-old dogs might include pugs and non-pugs, right? And then the 2-year-olds might again include pugs and non-pugs. So the pugs are kind of intermixed between other things. So they're not next to each other, it doesn't work. That's the only thing you need to remember. Okay, now a tricky one. I want pugs. I want them to be more than 10 years old, and I want them sorted by name. What do I need? Okay, come on. Venture something. Well, you might think it's something like this. Would this work? Breed followed by age followed by name. No, right? Because, you know, you're going to get the 10-year-olds before the 11-year-olds, even if the name would be sorted differently. Okay, how about the other way around? How about we do breed followed by name followed by age? Well, then they're sorted, but, you know, the 1-year-olds and the 10-year-olds are kind of intermixed. The answer is there is no possible perfect index that will handle this. Which means you can't send this query to the data store. It does not work. You know, the official rule is if you have an inequality filter, it must also be the first sort order. But that's not very easy to remember. The easier way to remember is there an index that would offer this? No, there isn't. You can't do this query. Now you're going to say, whoa, that sounds kind of annoying. I just can't do it. If I sent it to a normal database, it could do it. Well, yeah, but what a normal database would do is it would probably end up loading all of the pugs aged 10 or more, and then keep them in memory and sort them again and give you the first 10. Which is fine if you have 1,000 of them, but it's not fine if you have 1,000,000 or 1,000,000,000 of them, right? Now, keep in mind, in cases like this, you can do this yourself. You could just remove the sort order, load as many of them as you're willing to load, sort them in memory. Not that hard. But it makes it obvious to you that you're doing something that might not be so fast as you expected. Right? OK, so if you got all of this about indexes, it's pretty good news, because you essentially understand how indexing and querying works. There's one more kind of feature that I would really like to talk to you about. It's offset. So you can, when you send a query, you can say, hey, you know, I don't want the first 10 results. I want the next 10 results. Right? Every database has this, and the data store also has it. But now that you understand how it works, how could it possibly do this? How could it possibly find the 11th bug? Well, it's the only thing I can think of, and the only thing it could do is find the first one and then count down. But counting down and going through each of them, that's what takes time. It takes a lot more time than actually loading the bugs, right? So it turns out offset doesn't do any magic either. Loading 10 records with offset 100 is exactly the same as loading 110 records. So it's going to be several times slower than loading the first 10. So don't use offset. Don't use it. If you need pagination, because of course that's usually what people need it for. They want to, get the next page of results. If you need pagination, use cursors. Cursors, unlike in other systems, are brain dead simple. All they are is, remember this list, let's say this list? All the cursor is a bookmark for the position we got to in this list. That's it. It will behave exactly as you expect. You have the bookmark, you give it back to the data store, it will continue exactly from there efficiently. So whenever you want this kind of stuff, whenever you want pagination, second set of results, whatever, use cursors. They're really easy to use. Look at the documentation. They're just strings. You can store them. You can give them to the user. You can put them in a get URL. You can do whatever you want with them. Right? I don't want to go too much into it. The documentation is actually quite good on how they work. Now, I promised that I'll tell you about the one exception to the rule of the data store doesn't let you shoot yourself in the foot, and that's called Zigzag Merge. And Zigzag Merge is a bit of a newer feature in data store. The problem it's trying to solve, and unfortunately I don't have time to explain it all, it's kind of interesting. The problem it's trying to solve is you have a lot of properties for your data, and you want to make searches that combine all kinds of combinations of them, right? You have 20 properties, and you might search for all combinations of 5. What you gonna do? Are you gonna define all possible indexes? You run into some limits at some point, and it becomes very expensive to do all of this, and it's not very pretty. So zigzag merges work a bit like this. If we have these two indexes, right? One is by breed, the other one is by color. And we need to search for black bugs. Previously, I told you you can't. Well, it turns out you actually can do this. And what the data store will do, in short, is something like this. It'll find the first bug. Then it doesn't know if it's black, so it'll try to find it in the other index. It'll kind of notice that doesn't exist in the black section, but a Marty answer exists in there, so it'll kind of zigzag back into this one and find Marty. It's simpler than it sounds. I'm explaining it too fast, and it's quite efficient because it jumps over large chunks of the index in one step. Remember, jumping over things is efficient because this is sorted, right? But in theory, in practice, I can tell you from my own experience, these things work great. They rule. They're really awesome. They simplify your life if you have a lot of properties. In theory, though, if your data is really evil, like your data has a nice proper intermixing like this, but none of it is actually shared between the two indexes, you can get into a situation where this thing goes through every record like this and can't find anything. So those kind of queries can be slow, and sometimes you won't even know when. My recommendation, if you have a ton of properties and you allow very weird combinations, maybe the user can select the combination or anything like this, use Zigzag. If you have, if you just need 10 particular indexes, just define those 10 indexes. Don't use Zigzag. This is my recommendation. Right. So with this, we're done with indexing and querying. This is all you need to know to understand how indexes work, how queries are resolved, how fast the query will give you results, whether you can send a query. That's all. A couple of simple rules. But there's one other, there's two other words, one thing that is two words, that scare all new developers of Datastore. Can anybody guess what these two words are? The number of stars is correct, by the way. Come on, give it a guess. What's a really hard thing to get used to as a new developer in Datastore? Huh? Yes, actually, that's not what it says here. What it says here is eventual consistency. Eventual consistency is scary, right? Consistency, everybody kind of has an idea what that is. It sounds like everything is as it should be. That's my official definition. It's not the definition, but my definition is everything is all right. So that's what we want. But eventual sounds kind of scary. It's kind of like a friend comes to you and he says, dude, can I get 1,000 euros? And you say, yeah, sure. Will you give them back to me? Well, of course, eventually. And that doesn't make you feel very well or good, right? I mean, you're going, well, that's not a very strong promise. How am I supposed to work with that? And it feels like that's what Datastore is also giving you. It's saying, yeah, you know what? Everything will work fine eventually, eventually. So eventual consistency is scary, but it's not that scary once you understand how it works and what it actually does. So let's go into what happens when you change something. So in my example, I have my llama, and the owner, maybe it's not mine, because let's say it's Mike's llama, and Mike got kind of drunk, maybe, last night, and he had a spray can, and it's a long story. Essentially, we need to change the color to pink, and things happen. So if we're in this situation, what does the Datastore need to do? Well, it needs to do two things. It needs to fix this entry, right? And it needs to fix the indexes. Turns out there's another thing that it needs to do first, which is kind of write the transaction down. What needs to change? And the Datastore will tell you the transaction is done after step 0. Because it will be done eventually if it successfully did step 0, right? Now, what happens if I send a query here? Nothing special. It's as if the transaction never happened. I'll just get a brown Manuelito, right? Now, what happens if I send a query here? It's kind of weird, because if I ask for all the llamas, he's pink. But if I ask for all the pink llamas, because the index is not updated, he's not there. And if I ask for, the brown llamas, I'm getting Manuelito, but he's pink. So I asked for brown objects, and I got pink ones? How the hell do you program with that, right? It's scary. It gets even weirder if you're somewhere in the middle of step 2, because you can get in a situation where neither search for brown nor search for pink finds Manuelito. Or both of them do. Really weird. So, that's kind of hard to program with, right? But keep in mind, it's perfectly acceptable for some parts of your application. For instance, if you're showing users data that they could not possibly know has changed. For instance, Mike changes this color, right? Anne comes in half a second later and does a search for brown llamas. And she gets Manuelito in the list. Is this a problem? I mean, if she had pressed enter a second before, it would have been the correct results. Yeah, technically it's incorrect, but does it matter? Not really. But in some cases it does. Like if I just edited it, and then I look at it, and it's still the old one, I'm going to say, who the hell coded this application? Is this programming? So the solution to this is, now that you understand how it works, is to kind of ask for correct results. The first way you do this is by asking for a key directly. If you just ask for, give me Manuelito, the data store will give you the latest correct version of it. Yay. How does it do this? Well, we're going to get into it. But the problem is, if it can do this, why isn't it giving me all the results consistently all the time? Like, you know, if it can give me consistent results, why is it messing with me? Well, it turns out the way it can give you consistent results is your data, each piece of data, is stored kind of in a group of servers, of which one is the leader. And reads can happen on any of the servers, but writes only happen on one server. I mean, they happen on all of them, but one of them is the leader and he controls the writes. So that means that particular server can tell you for sure what the color of Manuelito is. Great. So why don't we do this? If I send a query for 20 llamas, why don't we do it for all 20 of them? Well, because, you know, they're spread around, and there's all of these groups everywhere, and your 20 llamas might be in a number of them, and they might be in different data centers, actually, and we need to kind of synchronize between all of them. And even if we did this, how would we know if there isn't a pink llama somewhere else? Maybe the index isn't updated. It would be really, really hard, well, let's say it's impossible or extremely slow to tell you if any llama anywhere is pink consistently. Now, your kind of thinking here should go, wait a second, if that is true, why can't I just put all the llamas on the same server? All of the llamas that say Mike owns, right? This way, this server can tell me exactly the right state for all of them. That's exactly what you do. There's a way in Datastore to group your entities into entity groups. They sound kind of fancy, doesn't matter. The idea is you put them together on the same set of servers, and that means any query you make on this set of servers will give you correct, consistent, perfect results. So you ain't going to get any pink, brown llamas or anything crazy. You're going to get everything right. And my first instinct when I saw this was, wait a second. Wait a second. So all I have to do is put the data on the same node? Well, why don't I put all of the data on the same node, right? I mean, is there a limitation? There isn't, at least not in terms of data size. These nodes will grow as needed to accommodate all of your data if you want. And as long as you just read it, everything is fine. But the problem is, remember what I started with? That this leader is the one that controls all the changes? Well, this leader is, you know, one guy, well, one server, right? It can only really do, because this is actually quite complicated, between 1 and 5 changes per second. So if all of your data does not change more than 5 times per second, go right ahead. Put it all in an entity group. You're going to get perfect consistency, and you're going to be perfectly happy. But if you, for instance, actually have more than one user, or you have a lot of users that are all editing this data, it turns out, you know, 5 changes per second is not going to cut it. The typical way to do it is to have every user's data in kind of a different group. This, you know, allows you to consist, like that user changes something, he will get correct results afterwards. Across users, it won't, but across users, as I gave you that example, it's usually not that obvious because, you know, other users don't know you just got drunk and painted your llama, right? So who knew? If all of this made sense to you, then, you know, really good news. You understand eventual consistency. That's it. There's nothing really else to say. You just group your data, and you get consistency in the groups. Where you don't care about the data, you put it in different groups. Easy enough. Now, does this mean it's easy to build a data model for your application? Nope. But it's never easy. I mean, you could use a a SQL database, and it'll still not be easy to find the right data model. That's still a design problem. Knock yourself out. But at least you're not going to wonder all the time, hey, what's going to happen, right? The thing you totally shouldn't do is treat eventual consistency the ostrich style, which is something like, your friend comes and says, dude, I looked at your code, and what about eventual consistency? No, I can't hear you. What is that? I don't want to know about that. Don't do that. Don't do that. Don't treat it as if it doesn't exist. Don't hope it'll go away. Neither of these things will happen. You should, actually, this is a very good advice as well, test for the worst case scenario. And there's a way, in any language you choose for your App Engine, there's a way to have your unit tests run in the worst case scenario mode, where none of this, like everything is as eventual as possible. And if your code works correctly in this mode, then you're going to be relaxed, because it's going to work fine in reality, where 99.9% of the time it's all good, right? One more piece of advice, and then I'll let you guys ask questions. Don't use the data store alone. There's a lot of other technologies available to you in App Engine for storing data. Blob store and cloud storage are good for big blobs of binary data that don't change that much. Memcache is great for tiny little pieces of data that change a lot, but you don't really care if they're lost once in a while. Cloud SQL is great for all the things, relational databases are great for. And Compute Engine allows you to run whatever you want. Whatever comes into your mind that's a storage system, just run it there. Actually, some of my most successful projects used 2 or 3 of these. So knock yourself out. Use them all when they're appropriate. Use the right tool. With that, thank you. And let's see some questions. Questions. There you go.
We have some time for a few questions.
Hey, your mic. Don't be shy.
Hello?
Yeah.
So you said that the search in the Bigtable is really quick since it's sorted.
Yes.
But it's really true because it's like logarithmic in a binary search. So is it really quick if we have like a big table? So even the logarithmic is not like fast enough?
Yes. The short answer, so the question, I guess you guys heard it as well, is it really that quick? I mean, if those big tables are really big, how logarithm isn't that, that fast? Well, it's definitely fast enough. Compared to the costs of the other things, such as, the communication between servers and so on, this will give you typically, numbers in the tens of milliseconds, 50 or something like that, which typically is fast enough. Of course, that's not a promise. It could be a lot slower because of many things. But if you need faster than that, and that's pretty rare, but sometimes you do need faster than that, consider Memcache. With Memcache, you'll get it significantly faster than that 99.9% of the time. And then once in a while, you lose the data, and you have to load it again, right? So yes, it is fast enough. There, I think.
I have a question. I don't understand why offsets are expensive, because to me it seems that it's just random access, where I should be able to find the first row and then just...
You mean in a sorted table, or?
Yeah, in the sorted table.
Right. Well, the idea is we're going to do... It does something... Wait, so is your question, how does it find the first key efficiently? Or no? I can't hear him, sorry.
Well, I kind of understand that finding the first row should be easy.
Right.
Then, and it should do the lookup by something like random accessing the Bigtable.
So you don't understand why it's easier to find the first one, right? You understand? Why can't I find the 20th one efficiently? Right. The problem is, remember, these are schema-less. So that means the amount of data in each entity is not fixed. I cannot easily calculate that, hey, if I want to jump 20 records, I should jump this many bytes. I have to literally read each of them to see when it finishes and then read the next one, right? So there's no easy way, no cheat code there. Now, of course, if it's really 10 records, it's not going to matter too much. But when it becomes 100 or your entities are really big, because you can have them be 1 megabyte, if you have a huge entity, then skipping over each of them takes time. Okay.
Okay, I'm afraid time is over. Thank you for your
presentation. Oh, and guys, I'm here all day, so if you have more data store questions or you're having problems with your application, just fetch me whenever. I don't understand Czech anyway, so I can't really watch the presentation. So thank you.